Welcome back, everybody, to the continuation of the exercise from page 110. This was the problem about population between California and the rest of the U.S., so we're looking at the top of page 111 here. And this part of the question is asking us for, number one, eigenvectors of the matrix that we found in part A, and then to give some information about how these populations in the U.S. and out in the US but outside of California and in California are behaving in the long run. So let's start by reminding ourselves of what that matrix A was. Okay. This was our transition matrix again that we found from part A. I'm just going to write it down again. Okay, and they want eigenvectors of this matrix. Now, this is a calculation we've done so many times. I'm not going to run through the actual calculation. You can look at my written notes if you want to see a few more details here, but I'm going to do this really quickly. Lambda 1 is 0.7 is going to lead us to an eigenvector that looks like 1, -1, and then lambda 2 equals 1 is going to lead us to an eigenvector of 2, 1. Okay, and we're going to use those to do a couple of things here now. So what they want is a general formula for the populations after n decades, right here. To do that, if you look back at the calculations that we did in part A, what we're interested in is taking this matrix A and being able to raise it to a power. That was the key to finding how the populations are behaving after a certain number of decades. But here's the thing. Raising a matrix to a power, that's not an easy thing to do. We'd have to take this matrix and multiply it by itself n times. For a 2 by 2, that might not be so terribly horrible, but if this were a bigger matrix, that's something that we definitely would not want to have to do. Okay, and so this is where diagonalization is going to help us. Okay, let's run through just how that works. So first thing I'm going to write down is the diagonalization formula from the last section. I'd like to give us a little bit more space here. So it looked like D equals Q inverse AQ. Okay, and D and Q had some special properties. They had to do with eigenvalues and eigenvectors. We'll talk about that in a minute. Let's first consider the problem of how do we take that equation and solve it for A? Because after all, it's A to the n that we're interested in. Okay, so algebraically, we can solve this equation for A by left multiplying by Q and right multiplying by Q inverse in order to cancel out the Q's that we see over on the right-hand side. You might remember this calculation from a couple of sections ago. So what this turns into then is an equation that looks like Q dQ inverse equals just A over on the right-hand side. All right. Well, we're interested again in the formula for A to the n. We can get that by taking Q dQ inverse to the n. And all that really means is that we're going to take Q dQ inverse and multiply it by itself n times. You might be looking at this equation and asking yourself, how is this easier than just taking A to the n in the first place? Well, there's some nice cancellation that happens here. Notice that in this big long product, we've got a bunch of Q inverse Q's times each other. So those are going to cancel into an identity. Those are going to cancel into an identity, and this keeps happening. This Q inverse and that Q are also going to cancel with the matrices that we can't see in the dot, dot, dot. And the question is, what's left here? Okay, well, if you look at this, all of the Q's that were on the inside canceled. We've got a Q at the beginning times a big string of D's, n of them to be exact, and then a Q inverse at the end. And so the advantage here is that it's a diagonal matrix that we're going to raise to the nth power, and that turns out to be a lot easier than raising the matrix itself to the nth power. So let's illustrate this now. What we're after is the populations after n decades, xn and yn. Remember again that these represent outside and inside California populations. From part A, we convinced ourselves that finding those populations is like taking the matrix a to the n and multiplying it by the initial populations. And we have this formula for a to the n up above. Q d to the n q inverse. So instead of writing a to the n, we're going to write that. Okay, so now we have to think about what are these matrices Q and D? Well, again, Q is a matrix that just has our eigenvectors as its columns. And to remind you, the eigenvectors are sitting up here. So Q is going to look like 1, -1. That's our first eigenvector. 2, 1 is our second one. And then D, that was a matrix that was diagonal and had the eigenvalues going down the main diagonal. So our first eigenvalue was 0.7, and our second one was 1. So those are the numbers that are going to be on the diagonal of D. We're going to get zeros everywhere else. That's raised to the nth. And then Q inverse is what comes at the end of this. Here, I'm going to need to use a formula that we talked about way back on page 72. You can look back. It was actually part C of page 72. It gave us a nice formula for the inverse of a 2 by 2 that looked like 1 over AD minus BC, which in our case is going to be 1/3. Okay, times this. To check this, you're going to need to look back at that formula on page 72. So feel free to pause the video if you want to and do that. And then at the end of this calculation, we've got x naught, y naught. Okay, so we've got some algebra to do here. Okay, and so the first thing, we've got some choices here as to how to proceed. But the first observation that I'd like to make is that this 1/3 that's sitting here, that's a scalar. So we have the freedom to move it if we want to. Scalar multiplication is commutative. So I'm going to choose to move the 1/3 way over here to the left and to multiply it into this matrix. If we do that, here's what we're going to end up with. Okay, and we'll go ahead and just write the rest of our equation down. Okay, so there's our next line of work. Okay, and now let's maybe take a minute to talk about this power. We need to take the matrix 0.7001 and raise it to the nth power, and here's the advantage of this method that we're using. Raising the original matrix A to a power, that would be difficult, but a diagonal matrix has a lot of zeros in it. And what ends up happening is when you take a diagonal matrix and raise it to a power, you can really just raise the diagonal entries to a power. That's all we need to do. Okay, you can think about that and check it if you like to. So that nth power that used to be there can just become an nth power on both of those numbers. That's going to be equivalent. Okay, continuing then with the calculation here. Let's write this first uglier matrix down. We'll leave that be for the time being. Okay, and let's do the same thing with the second one. 1 to the n is just 1. We might do that simplification. And let's go ahead and multiply these two things together. Okay, so just multiplying across, we're going to get x naught minus 2y naught, x naught plus y naught. Okay, but remember that x naught and y naught just represented initial populations. If you look on the previous page, you'll see that x naught was 270 million people. Those were the people that were outside of California, and y naught was 30. What that means is that we can actually get numbers for these two entries that I'm circling. They wind up being 210 and 300. Okay, so this is a lot of work, but we're getting closer here. Let's go ahead and multiply these two things together. Now that we've got numbers for those second pieces, this is going to look like 0.7 to the n times 210 and 1 times 300. Okay, almost there. Okay, if we do one more calculation, you can maybe double check my arithmetic on this part. So we'll take the first row times just this one column. And if we do that, we take 1/3 times 210, that's going to give us a 70. 2/3 of 300 is 200. And so what that winds up being in the first entry, if we write it out, is this. We just took the first row over here times the column here. We can do the same calculation down below and get this. Okay, so if we just kind of step back from this and take a look at what we have, we really have a formula for both of the populations, xn and yn. What we need to do is just to focus on the fact that xn, okay, the population of people outside of California, that has to be the first coordinate over here. And the same for yn, that's got to equal the second coordinate over here. So we've got two population formulas that we figured out. And so here's what we have. Xn looks like 200 plus 70 times 0.7 to the n, and yn equals 100 minus 70 times 0.7 to the n. Those are the population formulas that they asked us for. Okay, well, how are we doing with the questions they asked? I think that was a big piece that we just did. Let's scroll up and see if maybe there were some other things they wanted. Okay, and what I see is they also wanted to know what happens to the populations in the long run. We have not answered that question yet. Mathematically, if you think about it, finding the populations in the long run is about taking limits. It's like asking what happens to these populations as n goes to infinity. So we can do a little calculus calculation here. So taking the limit of this, and I'm going to do this in vector form. This is the limit as n goes to infinity of both of these two formulas that we have. And my question to you is, can you see what's going to happen here as n goes to infinity? The thing to maybe pay attention to are these two terms, because those are the ones that have n's in them. Notice what number it is that's being raised to the n. 0.7. What happens when you take a number that's less than 1 and raise it to the nth power? Well, it's going to get smaller and smaller, and it's going to go to 0. And so both of those second two terms go away. And what we wind up with is just 200 and 100 here. What does that really mean? Well, again, what we're seeing up here is populations outside, and down here populations inside. And so this is giving us what the kind of ending populations are going to be, the long-run populations both inside and outside of California. So we could summarize this by maybe saying something like this. In the long run, 100 million people will live in California and 200 million outside. Okay, and I think we have answered the question that they asked us.